So I will go straight because I have not enough time. So save time, I'd say I will talk about fracture mechanics and taking into account the mechanisms of crack propagation and initiation. And this work is done for two kinds of polymers. The first one is composite, and the other one is the matrix of this composite material. And this work comes from this paper that have been written with some colleagues here, where it has been reported that the mechanism of crack initiation and propagation is complex in the geometrical effects. And here I will talk just about and focus on the effect of the thickness, where there are some assumptions like plane strain and plane strain condition. And the other thing is the shape of the crack front, as you can see here for this work, where we can see that the thickness is not constant, and also the crack front is not straight. Okay, so to do that, I have this agenda. The first one, I will talk about the experimental methods. The second one is with the comparison with this laboratory test with tomography tests on polypropylene. And then the last is extension, the GSPP, if I have enough time, and going to the conclusion then. Okay, so the material is this one. This is a glass syntactic polypropylene, where we have this hollow microsphere right here, and the matrix is polypropylene. So this is the two materials that we'll talk about. From this material, we have here two kinds of geometry, so DNT-like specimens. The first one here for the laboratory test is DNT with a double notch. And this is for tomographic observation because the stroke of in the machine that you can see here is not enough to do such a test. So this is due to the laboratory specimen here, where we have measured, there is video acquisition here that you can see here, and also an infrared camera to check the head buildup. And this is the tomography at the synchrotron radiation facility at Soleil in France. Okay. Common test when we are doing test on the laboratory, you can see here the load versus normalized displacement, the applied displacement, and you can see here the shape of the specimen, the deformed specimen. You can see there that those are at the maximum load. Then when you are going to the load softening, you can see that there is some whitening at the surface. And then during the test, we can see now that there's a crack which has initiated here at mid-thickness and going to the end. And so you can see here that the shape of the crack is really very complex. You can see. So from this, we will focus on this crack in the following. We have this double notch. Okay, and going from this data, we have some fracture mechanics concepts that relates, in fact, the stress strain curve to the load versus the crack opening displacement curve here. So there, you can see that the stiffness here is controlled by the compliance, which we have the formula here that depends on the crack depth ratio and the Young's modulus there. Okay. The reference stress can give you an overview of where the load is here with respect to the stress on the stress strain curve. And this gives you this concept of limit load, where you have the formula for DNT specimen. I won't talk about the reference length, that's another approach, yeah. But you know that the fracture toughness is calculated with this critical J1 integral, the J1 integral. And you can see here that the thickness here is significant, of significant importance. And also the crack depth ratio is represented by here. Okay. All of these concepts are subjected to plane stress or plane strain assumption. So the agenda of the talk is right there. And so we have then transformed this curve to load versus opening displacement that have been measured, as I said, here on this crack on the here. And then the other curve is the crack depth ratio, which has been measured with this, the length of the remaining ligament here, and the thickness reduction that have been measured here, right here from the infrared camera, because we have turned a little bit the specimen in order to have the width and the thickness of the specimen to do that. Okay, so this is what happened at the limit load. You can see that first there is a thickness reduction here, and the crack is stationary. Second step, at the maximum load, the thickness reduction still continues to decrease. The crack still is stationary. And you can see also at that maximum rate, the temperature is, I would say, homogeneous. It's isothermal. So up to the maximum load, you have this isothermal situation of the crack, the remaining ligament. Now, as soon as we have reached the maximum stress, we can see here that there is the whitening here, and there is a head buildup on the cross-section there. And you can see that the slope of the crack thickness reduction is decreasing, and then start an increasing of the crack propagation here. And then we go through the up to the failure of the specimen right there. Now, going to the tomographic data. You can see you have, because we have to follow a plane in something which is deformed a lot. So we have located this microsphere here. It's well positioned in the remaining ligaments. And then we have measured here the crack front is right here, right? And then this is the length of the remaining ligament. So we have measured W minus A here, and the thickness reduction is here obtained at the mid-width of the specimen. And the COD, of course, is measured here, local COD. And this is the curve that that had been yielded. So here you have the normalized load with respect to the COD, but local COD, and the deformed specimen can be seen in the top. At maximum loads, at the limit load, you can see that the crack already started inside the specimen at mid thickness. So the crack is something that you can see here, and you can see the micro crack that comes in. Actually, it's crazy that you can observe here because there is some ligament of materials inside. Okay. 5 minutes in. Left. Oh, okay. So I have to do. Okay. So now at maximum load, you can see all of this tremendous, let's say, damage or crisis, and the crack have been already propagated from here. And so you can see all of this at the surface. Near the surface, you can see here the crack which is initiating from the surface, the crack front. And the shape of the crack in the top view is like this. And you can follow this thing that inside the channel, the crack have already is through the width already, whereas at the surface you can see not enough propagation. So this has been seen from the tomographic observation. We have compared here what happened from the tomography and the laboratory tests. There are some differences, and just to show you a few slides about the simulation that have been done. using this GTN model in order to take into account the porosity, so the void volume fraction that have been measured in the specimen. And this is the result. So we can see up to the maximum load that both are in good agreement, the experiments and the simulation. And also this, the thickness reduction has been also used in order to calibrate the parameter. And this is what happened during the crack growth, as can be seen here. So at this stage where the crack is running through the width, you can see here that it has also been simulated. So the last one is rapidly with GSPP. You have done the same thing. So laboratory tests, tomography tests have seen some differences. And here is the simulation. Going to the simulation. And you can see that here there is not so much thickness reduction. This means that there is a huge volume growth in the GSPP specimen. So the conclusion is we have done in situ tests using 3D imaging techniques. So this gives you 4D data set because this is on real time. Second, that you have fully 3D information on the volume surrounding the crack tip. We have measured the complete deformation gradients tensor measured experimentally. So this was useful to calibrate the material parameters using both local and global data. So the future we can see here. Thank you very much for your attention.